Namaskar. Welcome to Prakash on Basics. I'm Prakash Zog. We've been talking of radioactivity and its applications. The major use of radioactivity today is obviously nuclear energy, and that has two opposite natured applications. It is a major source of electrical power through nuclear reactors, which are also used to produce radioisotopes and obviously for other research work also. The harmful side of radioactivity obviously is the production of nuclear explosives, nuclear weapons. Previously, they used to be called atomic weapons and so forth. Technically, weapons of mass destruction by nuclear properties. Both these are based on a radioactive property of nuclear fission. I gave a brief idea of what it is when we talked of the properties of radioactivity. But if you're seeing this unit independently, I feel that we must have some background covered if we have to understand nuclear fission today. So I'll repeat and revise a few things. The name and major properties of any element are decided by its atomic number Z. That is the number of protons, which is also identical to the number of electrons present in it in a neutral state. Uh, I'm going to show you some information plus an equation later on, but I'll write it myself. It doesn't really make any difference. Uh, what we have here is uranium 238 92, and its isotope, which is the one that we are going to deal with quite often henceforth, which is uranium 235 92. That 92 below is Z, the atomic number, and A that is there is the 238 value, which is atomic mass number. N obviously is the number of neutrons that are present. So when I talk of uranium 238 92, it means that there are 92 protons, which is its atomic number Z. There are 146 neutrons to make the system relatively stable. And the total of these two is 238, which is known as the atomic mass number. If due to some factors there is a change that takes place and Z remains the same, but N, the number of neutrons, becomes different, then obviously Z plus N, that is A, will also be different. So such elements are known as isotopes. Since Z is the same, the name of the element is the same. So because in both these cases you have uranium 92 as the number of protons, so it is still uranium. But in one case there are 143 neutrons, so the total becomes 235. So that is uranium 235. And the other one has 146 neutrons, but Z is the same. So the total becomes 238. So that is uranium 238. These are said to be isotopes of uranium. There are others also, uranium 236, 234, and so forth. Let's not talk of them just now. Uh, one more aspect, that if this element that we are talking of and an isotope is radioactive in nature, then it is said to be a radioisotope. Everything associated with chemicals is based on the exterior number of electrons, and all this is within the nucleus. So radioactivity being a nuclear property, A, Z, etc., N are nuclear properties. The chemical properties of both these or any other pair of isotopes or multiples of isotopes is the same. But since the number of neutrons is different, their mass will be slightly different. So naturally, their physical properties or properties associated with mass, so many of them, will become slightly different. But the difference, as you can see, 238, 235, hardly any difference. So it's not going to be very large. To understand this, I think I should take up a couple of other examples. Uh, Let me talk of the most common substance that we have, which is water. And water is H2O. That hydrogen has a couple of other isotopes. Original hydrogen is just one proton. So nowadays, technically, hydrogen is known as protium. It has another isotope in which there is one more neutron present, and this makes it D21, and this is known as deuterium. And there is one more isotope in which there is only one proton but there are two neutrons. So it's 3 1 and T, which is tritium, but it's still written as H itself, hydrogen. And this hydrogen, deuterium, and tritium, or protium, deuterium, and tritium, form the three isotopes of hydrogen, and they make up water. So once we have water of this sort, suppose I make water out of all three of them and drink it, it's going to make absolutely no difference, because chemically they are all the same, because chemicals are associated with external properties. But the first one is said to be light water, and the other two are known as heavy waters. And this is a word that you must have heard whenever we hear about nuclear reactors and heavy water that is being imported from different countries or made in our countries and so forth. How heavy is it? If I drink this water, am I going to sink? Not really. If I have normal water, which is light water, and its mass is, let's say, 16 kg, the same amount of deuterium water, D2O, will turn out to be oxygen is 16 and deuterium is 4. So it's H2O or the D2O. So this is going to be 20 kg instead of the first 18 kg, because H2 and O will add up to 18 units. So if it is 18 kg of normal water, deuterium water will be heavy water, but it will be only 20 kg. And if I use tritium, it will become two more units more. So it will become 22 kg. So weight wise, it's hardly any difference, but property wise, things could be radically different. How? Maybe sometime. There are a couple of other isotopes that we've always heard of. We talk of ordinary oxygen and ozone. So ozone is said to be an isotope of hydrogen. And remember, sometime back we talked of carbon dating. Normal carbon that is all around us is carbon 12, 6 protons, 6 neutrons. But carbon 14 has 6 protons and 8 neutrons. And since it is radioactive, it is known as radiocarbon. And that is the one that we use to determine the age of so many different things. And in today's discussion, the most important one that we are going to talk of obviously is going to be uranium. And uranium has a number of isotopes, but the most predominant ones are uranium 235 and 238. 238 being far more than 235. There are many other isotopes also, cobalt 60, which is used in medical applications, and treatments, etc. But we'll come to that when we talk of medical applications. There is one more possibility. There is a possibility that both Z as well as N change. And the reason because of for this could be partially radioactive or some other activity. So the element becomes different because Z has changed. And such a change is technically known as transmutation. So the element has changed from one element into another because its Z value itself has undergone a change. Well, that's what isotopes and radioisotopes are, which is a part and parcel of the radioactivity that we are going to talk about today, and fission. Just a reminder, when I talked of properties, I told you what happens really in fission. It's like a laddu that breaks off partly to become a little more stable. And it could drop off in terms of small chunks, or it could just split into two. When it splits down into two parts, that's what fission is. And when radioactivity was being talked of right from Becquerel's time, they gradually started realizing that something like this could possibly be happening. Otto Hahn and Strassmann are the two people, Germans of course, are the ones who first discovered that fission does take place. And that was in on 19th of December 1938. And by January 39, Michener and Frisch was her nephew, uh, proved the physics that was involved behind these fission reactions. Fish is the one who named it as fission, like cell division that splits up and produces new cells. Uh, it was proved at this time that these reactions that take place are exothermic, exoergic reactions. Exo is to give out. So exoergic is the ones that give out energy. Exothermic are the ones which give out heat energy. So these reactions were known as exoergic and exothermic reactions. But they were basically nuclear phenomena. The energy obtained from this uranium at that time even was to be found out by two different methods. One was the one in which uranium 238 decays. That means small chunks drop off in the form of alpha, beta, and gamma radiation. This is a very slow, natural process, and it's not directly usable for us as it is. And the second one is associated with the isotope uranium 235. It doesn't split on its own, so it has to be made to split. Such processes are known as induced thermal nuclear reactions. And it could also result into a term that you must have heard sometime, chain reactions and so forth, fast chain reactions and so forth. We'll come to the fast chain reactions, etc., later on. So if I have to induce this breaking up process or fission, so what is fission? Fission is breaking down a heavy unstable nucleus into smaller nuclei in order to achieve stability. That is fission. Such atoms are said to be fissile atoms. Um, how do you achieve them? When studies were carried out, it was found that you could do it by bombarding the nucleus with either a proton or a neutron or a deuteron that we just talked of, or an alpha particle, which is the helium nucleus, or gamma radiation. All these possibilities are there and can be tried out. But what do we need to do? We have to talk of uranium 235, and for that, usually thermal neutrons are used. The word there is obviously thermal neutrons, and thermal here actually, I'm not going to go into details of its physics, but basically these are slow neutrons. Uranium 235 is the most common fission reaction that we know of. It requires neutrons of low energy, and these are the ones that are known as thermal neutrons or slow neutrons. How do you get them? There is another radioactive element known as californium, uh, C252, and it's a source of neutrons. These can be slowed down if required to the necessary form and utilized. Also, uranium 235 emits some amount of neutrons which can also be slowed down and used if required. Uh, their energy is pretty low. Uh, Long back when I talked of electrical quantities, I had told you of small units of electricity and energy. And the energy of these neutrons is 0.025 electron volt. But the neutron itself is extremely small, 10 raised to minus 27 kilograms. So that extremely small amount of energy is enough to give it a relatively fairly high velocity. But still we call it slow. And this slow velocity is about 2 kilometers per second. The velocity of sound is zero point 0.3 kilometers per second. You can imagine how fast these slow neutrons will be. Why do you need slow neutrons? Because when they go through the system, they must have enough time to interact with uranium 235. Otherwise, they'll go so fast, which are the fast neutrons that we will talk of later on. They go so fast that they will never have no chance of interacting with uh, the uranium 235. It's like a man rushing through a group of people and going so fast that he has no time to look at who's around. But then a slow person will say, hello, how are you? Interact with them and go to the next one and interact again and so forth. So you need to slow down things if you want to have an interaction. That's what happens. So you need slow neutrons traveling at 2 kilometers per second to interact with uranium 235 to result into fission. Understanding the fission reaction of 235 uranium is the basis of nuclear energy. It's a pretty simple equation actually, more like the equation that you must have studied in school, ninth standard, etc. Like hydrogen plus oxygen joining to form water and so forth, or carbon plus oxygen combining to form carbon dioxide and so forth. A very simple reaction. And so we need to understand this reaction. I could have typed and printed it out, but there are copyright issues. So let us forget. I am a teacher, so it's better that I write it down. So I've written down the equation for you. I'll show an equation, explain the equation as you look at it. This then is the equation. What it talks of is one uranium 235 atom nucleus colliding, being hit by a slow thermal neutron, that is one. This is the basic equation, first step. So what is going to happen? Neutron has no protons, so it has 0 below and 1 on top, because atomic A is 1, and this is 235 and 92. So what happens initially is when it interacts, they combine. So this 92 remains as it is, but this becomes 236. But this, then obviously this is also an isotope of uranium. But this happens for an extremely small amount of time, and immediately it splits up. Uh, when it splits up is the second line that we have. It produces krypton 89 and 36, barium 144 and 56, and in addition, because the total number has to match out to that 236, so there are three more neutrons that are left, and these are extremely fast moving neutrons that are produced. So in this nuclear reaction, when a fast moving neutron hits the nucleus of a uranium 235 atom, it breaks that uranium 235 into barium and krypton, plus in addition it produces three more extremely fast moving neutrons. There are some more other types of reactions also, but usually if you look at the values that are there, 56 30, 56 36 and so forth, you will realize that they are roughly in the ratio of 3:2. That's what usually happens. There could be also be a possibility of some energy being liberated in the form of gamma radiation. But there is one more reason why all this happens. There is obviously something known as binding energy per nucleon, and another factor associated with an equation that many of us know by heart without being from science, and which is E equal to mc squared. How does that come into picture here? If all the uranium 235 that is here, which is only one atom, and only one neutron, if you take their combined mass, and if you take the combined mass of all these, this mass is slightly less than this total mass. This loss in mass is known as mass defect. And then this mass defect gets multiplied by c squared. C is the velocity of light, which is 3 into 10 raised to 8 meters per second. And this E equal to mc squared. Mass defect, c squared is 3 into 10 raised to 8 multiplied by 3 into 10 raised to 8. And all that energy is the one that is given out as nuclear energy in this reaction. This energy is given to the barium nucleus, the krypton nucleus, and the three neutrons in the form of kinetic energy. Kinetic energy is energy of movement. This equation is half mv squared. Let's not bother about it just now. So, and this happens in an extremely short amount of time, in picoseconds. And uh, so the energy is given, and the neutrons are minuscule, extremely small as compared, understand, 238 size and one size. This is going to be extremely small, and these are going to be all the atoms that are going to be around. So there's hardly any blocking for these these three neutrons. They are anyway very fast. So they immediately shoot out from that reaction area and go away. But the barium and krypton atoms are pretty big, and there is hardly any space in between for them to move. So they immediately come to rest. It's like applying very strong brakes and it stops. And you know what happens when a vehicle stops? All that screeching results into the tires heating up. All that energy that they had is immediately converted into heat. And that is the heat that is released during the reaction. So it is the mass defect resulting into new kinetic energy, which because of its being stopped gets converted into heat energy. And it is this heat energy that is generated during this particular nuclear reaction. They lose their velocity in a fraction, that is a picosecond. Pico is 10 raised to minus 12. Remember the numbers I taught you all about. A picosecond is 10 raised to minus 12. That means a millionth of a millionth of 1 second. पलक झपकते ही वगैरह is too large. We have hardly any movement that is seen, and in that picosecond, light also travels a very small distance in this particular amount of time. I will talk of that sometime later. So immediately that energy is released and the reaction is over and the heat has been liberated. How much energy is released? It is one uranium-235 atom interacting with one neutron. Their mass defect releases an energy which is in terms of uh, electron volts. If I talk, it is equivalent to 200 million electron volt. Even if I say million, that electron volt itself is very small. So the whole thing, if we talk in terms of joule, is 32 into 10 raised to minus 12 joule. It's extremely small amount of energy, hardly anything. So uh, how does this provide energy that we are talking about? The reason is very simple. The uranium-235 atoms, their number itself is extremely large. In 1 cubic centimeter, if you take an average density of a normal object, there are close to around 10 raised to 24 atoms. 1 followed by 24 zeros. Population of India is billion. So billion, billion, million is getting close to this particular number. So the number of atoms available itself is very large. Number of neutrons available is also very large. So the net amount of energy released in the process is pretty large. There is no sense in just saying pretty large and this is very big. There should be some number. And this is talked of in terms of uh, energy density of this fuel that is going to be used. If I use uranium 235 as a nuclear fuel, 1 gram of uranium 235's fission releases heat equal to 4.5 tons of good quality coal. 1 kg of coal is enough to heat up, boil water and so forth and have some good amount of rest. We are talking of 4.5 tons, that is 4,500 kilograms of coal in 1 gram of uranium 235. So you can imagine the energy density of this particular fuel. And that is why it is important. And realize one more thing, it has got only converted into another material. What is really being lost is only the mass defect. And that mass loss is extremely small. So it's practically remaining the same, only getting converted into another element because of fission reaction. And it is this heat that humans have put to use by a principle known as thermodynamics. Thermo is heat, dynamics is motion. So you have thermodynamics from this heat that generates the electricity. And that is obviously something that is associated with nuclear reactors. So that's what we will talk of next time. How does this energy get utilized? And is that all from the uranium 238 and 235 that is there around? So we need to know about this uranium also. There's one more thing that I mentioned, which is very important, and that is those three neutrons, fast neutrons that got away. They have a lot of energy. So that energy was put to use. And not just the energy, but the way they are moving is also put to use. And that is also very important. But that is something that we will talk of a little later. Those three neutrons, fast neutrons, are equally important. So that's how fission takes place. It can take place in other elements also, but they're not really very common. Uranium 235 is the only one that we usually talk of. There are other things like plutonium and thorium and others, but we will talk of them a little later. Thorium important for Indians because we have a large source of thorium, and we'll come to that later on. If you liked whatever I have said, uh, try and look up the equations. I have shown them to you. They're not really very difficult, very pretty simple. Uh, you can see the equation somewhere. I hope it will give you a clue as to what really is happening in the process. Uh, if you press the bell icon, you will be able to get a notification as to when the next lecture would come up. Pass on this knowledge to your younger generation and to others who would be interesting. Because Jyota se Jyota Jalate Chalo, we just have to pass on and share knowledge. Like and subscribe to this channel. And till we meet again for the next part of this, or the Veds and Upanishads that we have been talking of. Till then, this is Prakash Zog saying Namaskar.